Okay, hello everyone. Okay, so we've been looking at alkenes and alkynes, specifically reactions of alkenes and alkynes. And I'm going to share my screen. Okay. One reaction we talked about, which was from the previous chapter, was the acidity of terminal alkynes. We have a triple bond at the end of a chain, like this. We can remove this proton with sodium amide, NaNH2, which is the conjugate base of ammonia. This is carried out in liquid ammonia as a solvent. NH2 minus donates a pair of electrons to this hydrogen, and then hydrogen gives away both of its electrons in this bonding pair to the carbon. Okay, carbon was neutral, a pair of electrons moved toward it, it's now negative. NH2 minus, when it picked up an H and a plus, it became ammonia, which also happens to be the solvent. Okay, this will not work with hydroxide as the base because water is a stronger acid than this terminal alkyne. Whereas in the case of ammonia, this is the alkyne is a stronger acid than ammonia, so this works. Okay, later on in the semester, we'll see why this is particularly useful. Okay, once we get this anion, there's a number of things we can do with it, including building a carbon chain. I'm going to go ahead and erase that. Okay, most of the reactions in this chapter involve some kind of addition. Right, so the general pattern is we have an alkene. This also works with alkynes. And then we have some reagent, which I'll designate as XY. Okay, where X adds to one side, Y adds to the other side, and there's no double bond in the product. All right, we also introduced the term regioselectivity. Regioselectivity means that a particular positional isomer is favored. So regioselectivity indicates that a particular positional isomer is preferred or sometimes exclusively formed. And as an example, let's take propene. Well, we add HCl to propene. Okay, does H go to carbon number 1 or does it go to carbon number 2? Well, we can predict that using Markovnikov's rule. Markovnikov's rule, one way of stating it is that the rich get richer when it comes to hydrogen. So carbon number 1 already has 2 hydrogens, carbon 2 has 1, so carbon 1 is richer. So carbon number 2 hits the chlorine. CH2 becomes CH3. Okay, and not the other way around. So this is the product that we get. Okay, so this is the general pattern, and most of the reactions are specific examples of this. Okay, once again, here is a summary of the different types of addition reactions. Okay, hydrochlorination or hydrohalogenation in general is what I just showed you. Hydration, where we add an H and an OH. Okay, these are both regioselective. The rich get richer when it comes to hydrogen. Halogenation, most commonly it's bromination, but you can also add chlorine. It's 2 chlorines, so this is not regioselective because it doesn't matter which bromine or which chlorine goes to which carbon. We'll look at hydroboration, which is a little bit different. It's actually an intermediate in preparation of alcohols. And then we'll look at hydrogenation, which is the addition of hydrogen. Okay, so we reviewed, let me go back. We reviewed energy diagrams, what activation energy is, what endothermic versus exothermic is. Okay, and most of these addition reactions will involve an intermediate, which is a local minimum. And in this example, the first step has the higher activation energy, so it's going to determine the rate. The second step will be much faster because there's a lower activation energy. Transition states are very short-lived, very difficult to observe, whereas in some cases intermediates can be observed and isolated. Okay, in this example, since the product energy is lower than the reactant energy, this is overall an exothermic reaction. First step is endothermic, second step is exothermic. It's exothermic overall. Okay, I'll go ahead and mention some of the common patterns. One is to add a proton, and actually this is transferring a proton. Okay, so we add a proton to ammonia. Okay, we can remove a proton. This is just the reverse of what we saw a moment ago, also transferring a proton. Okay, notice how we use the arrows. We always go from negative to electron deficient. Okay, we can donate a pair of electrons to form a new covalent bond. And again, it's always negative to positive. Rearrangement. Okay, this is very common with carbocations. Okay, what's happening here is that hydrogen is pulling out its electron pair, moving over, and donating that pair to this carbon. Okay, what that does is it produces a more substituted, a more stable carbocation. Okay, the more carbons you have bonded to that positively charged carbon, the more stable it is. Okay, this is what's called a secondary carbocation. This carbocation is directly bonded to 2 other carbons, whereas this one is directly bonded to 3. Okay, and then this was just the opposite of forming a covalent bond that we saw a couple of slides ago. The bromine leaves, taking a pair of electrons with it. Okay, since carbon lost a pair of electrons, it's now positive. And since this bonding pair became a non-bonding pair, now bromine has a negative charge, so it's a bromide ion. Okay, so these are some of the electrophilic additions that we looked at last time. Okay, the first two, hydrohalogenation and addition of water with a catalyst, both follow Markovnikov's rule. Okay, they are regioselective. Okay, this is one I just showed you with propene and HCl. Okay, we only get the 2-chloropropane, not the 1-chloro. Okay, and then we went through some other examples of Markovnikov's rule. All right, in this alkene, carbon number 1 has 2 hydrogens, carbon number 2 has none. So the rich get richer. The other position gets the iodine, and the other isomer is not observed. Okay, so here's another example. This does require a catalyst, and that's because water is not acidic enough. So using sulfuric acid as a catalyst, H goes to carbon number 2 here. Okay, there's already 1 hydrogen, and there's none at this position. Okay, so we get this alcohol and not this one. Okay, we practiced these last time. I'm going to go on to the next slide. Okay, so why does Markovnikov's rule work the way it does? Well, it has something to do with carbocation formation and forming the more stable carbocation. Okay, so if we start out with 2-butene, this is a nucleophile, that is an electron pair donor. It donates a pair of electrons to hydrogen. Hydrogen gives away its bonding pair to chlorine. We get this carbocation. Okay, there's no incentive for this to rearrange because the only other carbocation you could get would be a secondary or a primary. Okay, so once we form this, we have a negatively charged chloride. So opposite charges will attract. Chloride will donate a pair of electrons to that empty spot on the carbocation. And then our product is 2-chlorobutane. Okay, this is a 2-step reaction. The first step, formation of the carbocation, is rate determining. The second step, okay, since these are oppositely charged ions, they come together very quickly, and so there's a low activation energy, and overall this is exothermic. Right, this is the tert-butyl cation, and this is its 3-dimensional structure. Okay, the central carbon has a trigonal planar geometry. These 4 carbons are all in the same plane. And then there's a vacant 2p orbital that's perpendicular to the plane of the ion. A carbocation is a species containing a carbon atom that has 3 bonds to it. There are 6 electrons in the valence shell, and it carries a plus charge. Okay, so it does not have an octet. The bond angles around this positively charged carbon are approximately 120 degrees. Okay, the hybridization, okay, which of course corresponds to the geometry, is sp2. And going back for a minute, these sp2 orbitals form sigma bonds with these other carbons or hydrogens in the case of other carbocations. Okay, so there was a 2s atomic orbital. There were 3 2p atomic orbitals. We hybridized or mixed 2 of the p orbitals, so there's one left over that was not hybridized. And that's the vacant orbital that lies perpendicular to the sigma bond framework. It's empty, it has no electrons. Carbocations are electrophiles, that is, they are electron-loving. Electrons have a negative charge, carbocations have a positive charge. They're also referred to as Lewis acids. Okay, they accept electron pairs. A tertiary carbocation is more stable than a secondary carbocation, and it requires a lower activation energy for its formation, so therefore it's formed faster. A secondary carbocation, in turn, is more stable than a primary carbocation, and it requires a lower activation energy for its formation. Right, so this is the order of carbocation stability. Tertiary is the most stable. Okay, then secondary, of which isopropyl is an example, then primary, then methyl. Methyl and primary actually are so unstable that they are never observed in solution. Okay, so why are tertiary carbocations more stable than secondary? Okay, one reason is what we call the inductive effect. And as a result, the polarization of the electron density of a covalent bond as a result of the high electronegativity of a nearby atom. And so the electronegativity of a carbon atom bearing a positive charge exerts an electron withdrawing inductive effect that polarizes electrons of the adjacent sigma bonds toward it. Okay, thus the positive charge of a carbocation is not localized on the trivalent carbon, but rather it is delocalized or shared over nearby atoms as well. Okay, and this is a general principle which applies to a lot of things in organic chemistry, and that is the larger the area over which the positive charge is delocalized, the greater the stability of the cation. All right, so here's a methyl versus a tert-butyl. And tertiary carbocations are more stable and require a low activation energy for their formation than secondary carbocations. Primary and methyl carbocations are so difficult to form that they're never observed in solution or in any of the reactions we will discuss. Okay, so what's happening here is, okay, on the left we have a methyl carbocation, and okay, it's pretty unstable. You can see they've shown the charge distribution, the charge separation. Okay, here is a tert-butyl carbocation. Okay, this is what we mean by the inductive effect. These methyl groups are donating, they're pushing electrons through the sigma bond to help stabilize that positive charge. Okay, when we got 3 of them, okay, that really helps the stability. Okay, so the methyl groups donate electron density toward the carbocation carbon, which delocalizes the positive charge. Calculations show that the more substituted carbocation has a greater positive charge delocalization. Okay, this is related to Markovnikov's rule. Okay, the chemical basis for the regioselectivity embodied in Markovnikov's rule lies in the relative stabilities of carbocation intermediates. The reason why the proton of HX adds to the less substituted carbon of the double bond, or the carbon that has the most hydrogens, is that this mode of addition leads to the more stable carbocation intermediate. Markovnikov lived in the 1800s. Carbocations were only observed in the 20th century, but they help to explain why Markovnikov's rule works the way it does. Okay, so when we add a proton to the alkene functional group of propene, we can either get a primary or a secondary. Okay, and we've already said there's a lower activation energy, and the secondary carbocation is more stable. And so this is the product that's formed, the 2-chloropropane. Okay, next let's look at addition of water. Okay, this follows a similar pattern, but there's an extra step, and that involves the role of the catalyst. Okay, so H and OH are added to an alkene. H goes to the side that is less substituted or has the most hydrogens. OH goes to the other side. Okay, so water is not acidic enough for this first step. So if you add an acid catalyst, a strong acid like sulfuric acid, the alkene picks up a proton from hydronium, and the more stable secondary carbocation is formed. Okay, what happens next is water adds to that middle carbon. We get what's called an oxonium ion. All right, the reason it's water and not hydroxide, okay, if we think about it, this is probably 20 to 50% sulfuric acid, and so the hydroxide concentration is going to be negligible. Okay, so water adds, and then we have excess water. So water will use a pair of electrons to act as a Lewis base and a Bronsted base. It's going to remove this extra proton. This pair of electrons will shift onto the oxygen. Oxygen was positive. It gained this pair of electrons, so now it's neutral. And we get back hydronium. Okay, so hydronium was a catalyst. We put one in at the beginning. We got one out at the end. All right, so here we have a problem. Account for the fact that the acid-catalyzed hydration of alkenes can be used to prepare both secondary and tertiary alcohols, but with the exception of ethanol, it cannot be used to prepare primary alcohols. Okay, so let's look at this. Okay, so this is what we would predict. Right, so we have 2 hydrogens on carbon number 1, so that gets richer, and OH goes to the other position, and we do not get the other regioisomer. Okay, so let's draw the structural formula of an alkene that undergoes acid-catalyzed hydration to give each alcohol as the major product. Okay, more than one alkene, sorry, may give each alcohol as the major product. Okay, so let's take a look at A. Okay, so it looks like two alkenes would work here. Okay, we want to remove H and OH from adjacent carbons. Okay, so it looks like that one would work. Okay, this is an equivalent position. That would give you the same alkene. And we should be able to remove an H and an OH from these two positions. Okay, and this would give us the correct regioisomer. H would go here, OH would go here. Okay, taking a look at B. Okay, again, it looks like we should be able to use two different alkenes here. Should be able to remove H and OH. Like that. And the other side would give us the same product. We have the double bond over here. Okay, we should be able to remove H and OH from these two adjacent carbons. Okay, so starting from this alkene, we can make that alcohol. All right, letter C. Okay, and again, it looks like there's two possible alkenes that we could use here. Okay, this one, 1-methyl cyclopentene. The other one would be adding this H and OH. Okay, so this would be the other alkene that we could start with. Okay, and then letter D. Okay, these are called beta hydrogens. Hydrogens on the next carbon over. Okay, so we can form our double bond here, or here, or here. Okay, so it looks like there's three possible alkenes that we could use. We have this one. We could have this one. Or this one. All right, so this is actually very similar to hydration, except we are using methanol as our solvent instead of water. And this would follow exactly the same mechanism. Okay, notice the historical perspective here. Treatment of 2-methylpropene with methanol in the presence of an acid catalyst gives terbutyl methyl ether. At one time, this compound was added to gasoline to increase octane rating. In fact, this had approximately 120 as the octane rating. Okay, it burned very smoothly. Due to environmental concerns, however, it's no longer used for this purpose. Okay, when it got out into the groundwater, it was very difficult to separate from the water during the treatment process. Okay, so this would be nearly identical to the addition of water. Start off with methylpropene, and sulfuric acid and water will give us hydronium ion. Okay, so the double bond is electron rich, and it's an electron pair donor. This pair of electrons will shift up onto the oxygen. We will get our terbutyl cation. And in the next step, methanol, instead of water, will add. So it will donate a pair of electrons to the positively charged carbon. Okay, oxygen now carries a plus charge since it has 3 bonds. And I missed a group there. Okay, and this is done in excess methanol. Okay, so another methanol, or you could also use a water, it doesn't matter. Okay, we produced water in this first step. Okay, so methanol or water will take this extra hydrogen, and then our product is methyl terbutyl ether. Okay, next we're going to look at addition of chlorine and bromine. Okay, this can be carried out either in pure reagents or in an inert solvent such as dichloromethane, also called methylene chloride. Okay, so bromine adds to the double bond, and we get, in this case, 2,3-dibromobutane. Okay, there's no double bond in the product. Okay, now we're going to introduce another term. We talked about regioselective a little bit ago. This particular reaction is stereoselective. Okay, so it's not regioselective because it doesn't matter, okay, which side gets gets a bromine because each side gets the same, but it is stereoselective. One particular stereoisomer is formed or destroyed in preference to all others. Okay, in the addition to a cycloalkene, we only get the trans product, and so this is called anti-stereoselectivity. Okay, what we have in this picture here is a simple chemical test. Okay, if you have an unknown compound and you think it might have an alkene functional group, okay, one thing you can do is you can add bromine or bromine solution, which has this dark red-brown color. And if that red-brown color disappears, that's an indication that the bromine added, because these dibromoalkanes are typically colorless. Okay, so this is probably colorless. Well, this is colorless. Bromine is red-brown, and then the product is colorless. Okay, so why is it stereoselective? All right, so in the first step, double bond acts as an electron pair donor, nucleophile. While bromine is a nonpolar molecule, there is an induced dipole that occurs. The electrons are repelled over to the other side. So it attacks and forms this bond. The other bromine breaks off to form a bromide ion. And then bromine attacks the carbocation and forms this three-membered ring. This is called a bromonium ion, or if it's chlorine, it's a chloronium ion. And then the bromide ion, Br minus, has to attack from the back side. Okay, it shows attacking this carbon, but it could also attack the other carbon. Okay, so when it does that, it forms a bond here. This bond breaks, and so the two bromines are 180 degrees apart in the product. They're anti, and they are coplanar. Okay, using the Newman projection, that's what this shows. They're 180 degrees apart, anti-coplanar. Okay, so we only get the trans isomer, not cis and not a mixture of cis and trans. All right, so when cyclohexene adds bromine to it, and all you have to do is just mix these, they'll react immediately. All right, initially we get the trans diaxial, but then it equilibrates by ring folding until we get the trans diequatorial. Okay, the next aspect of alkene mechanisms that we'll look at is carbocation rearrangements. Okay, so as we've seen, the product of an electrophilic addition to an alkene involves rupture of a pi bond and the formation of two new sigma bonds in its place. In the following addition, only 17% of the expected product is formed, and the reason is rearrangement. Okay, so if we start out with 3,3-dimethyl-1-butene, we add HCl, rich get richer, hydrogen goes to number 1, chlorine goes to number 2, but we only get 17% of this product. Instead, this is the major product. It is 2-chloro-2,3-dimethylbutane. Okay, notice the carbon skeleton is different. So a rearrangement took place. Okay, in the rearrangements that we examine, typically either an alkyl group or a hydrogen atom migrates with its bonding electrons from an atom to an adjacent electron deficient atom, as illustrated in the following mechanism. And this type of rearrangement is called a 1-2 shift. Okay, so let's look at how that occurs. Well, the first step is, as you would expect, double bond picks up a hydrogen. According to Markovnikov's rule, hydrogen goes to position number 1. We get a secondary carbocation on position number 2. Okay, but then we have a rearrangement. Right, this methyl group will migrate. Okay, it pulls out its electron pair, leaving an empty spot, and it plugs them in at this position. And the driving force for this is going from a secondary to a more stable tertiary. And once we get this, then chloride adds to give the major product. Okay, some of the chloride will add to give this minor product from this intermediate. Okay, so this shows the chloride forming a new covalent bond with the tertiary carbocation. Right, we can also get rearrangements during acid-catalyzed hydration of alkenes, especially where the carbocation formed in the first step can rearrange to form a more stable carbocation. Okay, in this case, it would involve, rather than a methyl shift, it would be a hydride shift. So hydrogen would move over, and this would be the major product. Okay, here are some other rearrangements that could take place. We are out of time, so first thing Monday, we'll take a look at proposing a mechanism for these two reactions. Okay, so I will see you later. See you Monday. Have a good weekend.